Okay, first of all, let's review what we learned last week. Okay, right now we are talking about signal to noise ratio and also how we measure the SNR in order to evaluate the performance of the system, right? So SNR is the very important measure if you want to evaluate the performance of a communication system, right? If the SNR is high, that means our system has a good performance. If SNR is low, generally the performance is very bad. Okay, so the SNR is in that way is a very important measure. And in our system, we measure the SNR at two different places. Right? One is what we call as a pre-detection SNR, and the second is a post-detection SNR. And the reason that we called it pre-detection and also post-detection SNR is because that this pre-detection SNR is measured before the demodulation, before the receiver, okay, before the receiver procedure, which means that as soon as you receive the signal at the antenna, you measure the SNR. That's pre-detection SNR. And post-detection SNR is measured after you do all the demodulation process. Okay, so this one, pre-detection SNR, you grab the signal over the air and measure the SNR right away. So therefore, the signal you measure is a passband signal. Okay, so we are looking at the passband signal and measure the power. That's the signal power, divided by noise power, still in the passband. So this pre-detection SNR is measured with the passband signal. However, in post-detection, you are going all the way through the demodulator. So at the end, you are going to recover your message. So therefore, this post-detection SNR is measured at the baseband. Okay, there's no carrier. In this case, you have a carrier signal. This is not carrier. There's no FC because we already demodulated, right? Our message is already there. I mean, our original message, we recovered it already. So the measured SNR is measured after the demodulation. Therefore, it is a baseband. So now for the system, we're going to looking at many different systems. First of all, we looked at the DSP system, right? Double sideband. It's an amplitude modulation. We know that the DSP signal over the air looks like this, right? This is a carrier component multiplied by message because this is amplitude, DSP modulation. So this is a modulated signal. So this is the signal over the air. So now you get this signal over the air and measure the SNR right away. So that's right here. So if you do that, that's going to be pre-detection SNR. Okay, so let's look at the pre-detection SNR. Now you get this ST, this one, ST, and measure the signal power of this ST. This is a signal, right? So measure the signal average power. How can you do that? Expectation, because we are taking average, and then S square, because we are calculating the power, right? S square means power, and expectation means average, time average. So this is how to calculate the average signal power. And how to do that is you need to do S square. So this is our ST. So you put them here, right? The same thing. We just, in order to see it clearly, I just separate it, but MT was here. So you do square, and then expectation. Okay? Once you do that, then you're going to get this. Okay? Simply, as I said, if you square of this and do integration, what that means is when you square it, AC square, MT square, and then expectation, and cosine square expectation, that becomes 1 over 2, right? Remember that? That's this cosine term will be gone, and that will be changed to 1 over 2. So eventually, the output you're going to get is AC squared times P. P is this one, divided by 2. And this one, you know that this is the average power of your original message. Your original message has a power, some power, right? That's P. Okay, so this is a signal power over the air. Okay, now that we know that this is the power spectral density of your noise or your signal, actually. So because remember that AWGN, WT, remember that we have two different noise, right? WT and NT. Remember that? WT is the true white noise, which means that if you look at the power spectral density, it's going to be flat. But when such kind of noise comes into our receiver always has a bandpass filter, right? Let's go back here. Your noise is added, but whenever you receive the noise to your antenna, the first thing happen is the bandpass filter. So you go through the bandpass filter. Now the noise changes to NT, right? So therefore, your NT has this power spectral density, and there is a bandwidth. This bandwidth is your bandpass filter bandwidth. Because we go through the bandpass filter, your bandpass filter has some bandwidth, right? So therefore, this is a power spectral density of your noise, NT, right? So you can simply calculate the area under this power spectral density. That's going to be like N naught BT. So this is your noise power. So we already calculate the signal power over the air. Now this is the power of your signal over the air. This is a noise power. So simply this one divided by this will give you this SNR. This is a pre-detection SNR. So pre-detection SNR is pretty easy to calculate. Okay, that's it. It's pretty very simple. Now, secondly, we need to calculate the post-detection SNR. So this is the SNR we measured after the demodulation. So this is what happened at the baseband. So in order to eventually go to the baseband, what we need to do is we need to change our NT, noise NT, into this baseband representation. Because NT is a passband, still in passband. This is a passband, right? This signal is around your carrier frequency. So this is still passband. We cannot go passband, right? Because we need to put this one bring this one into the baseband and put it into demodulation. So therefore, we're going to change the representation of the NT into this way. So once you change this, now the NT is a passband, but NIT, NQT, these both are baseband representation, right? These are both are baseband representation. So once you change the NT into this, now you can go same way. The first thing happen at the receiver is that you are multiplying your cosine carrier. So you're going to multiply cosine carrier here. So ST times cosine, and also this baseband representation of the noise times cosine. Okay, because that's the first thing in the coherent detector, right? We are talking about coherent detector. So inside the coherent detector, you're multiplying cosine. That's good. That's the first step to do. So multiply cosine like this. Okay, here. Then we know that eventually when you multiply cosine, our ST was ACMT cosine. So therefore, when you multiply cosine again, that's going to be like ACMT cosine square. We have ACMT cosine square. And here is again cosine square, but this one is a sine times cosine, right? Because we multiply cosine. So therefore, using this identity, when you have a cosine square, we know that cosine square will be changed to this. Sine times cosine will be changed to this. We know that. So using these two identity, we can change this into this way. Now, after you multiply the cosine inside the coherent detector, the next thing to do is go through the low-pass filter. So when you go through the low-pass filter, now this high-frequency component, also this high-frequency component, these are all gone, okay, all dropped. Now, what is left over is only this term. So this is what is passing all the way through, and what you're getting here at the end of demodulation is only this one. So we're going to get only this. That's this one, this one, this one, this one. So that is YT, which is here. So that's the output of the demodulation. Now, when you look at this output, right, we have a signal part. We also have a noise part. Okay, we have two different parts. So now, how do you calculate the SNR? You're going to look at the signal part and do square and do expectation. That's going to be signal power. Same way for noise, again, you do square and then expectation. That's going to be noise power. So you can separately calculate the signal power and the noise power and do a division. That's going to be your SNR. So once you do that, you're going to get this result. So that is your post-detection SNR. Okay, post-detection SNR. So when you compare this post-detection SNR with the pre-detection SNR, now you know that this post-detection SNR is twice better, twice higher than the pre-detection SNR, which means that when you go through our coherent detector, now SNR gets better. Okay? When you grab the signal over there and measure the SNR, but that's 2 times worse. If you grab the signal, put it into the coherent detector, our receiver, and the output of the coherent detector has a double SNR. It's 2 times better SNR. That's what that means. Okay? So that was the result that we discussed last time. Now what we're going to talk about today is another example. The first modulation we learned is this one, right? This is also amplitude modulation, but this is the DC added amplitude modulation. Okay? Remember this one? That was the first modulation we learned, right? So at that time, if you do the amplitude modulation and you add the DC, we have this signal over the air. Okay, that is a signal over the air. Now, first thing to do is, again, in this case, we want to look at what is the pre-detection SNR. So pre-detection SNR, same way. You grab the signal over there and then square the expectation. So this is a signal over there. Now let's do square and then expectation. Okay, once you do that, so that's what you do all the time. So this is a ST when you do DC added modulation, amplitude modulation. So this is a signal that we transmit over the air after modulation. Now what we want to calculate is this, because this is a signal power. So we need to do square expectation of square of the whole thing, then AC square 1 plus KA square, and also cosine square. So that's what we need to calculate. When you calculate this, right, easy way to do it is, this is a constant, AC is constant, so you can bring the constant out. Now, this part and this part is independent. So you can separate these two because these two are independent. You can do it this way, right? The expectation of the whole thing is same as AC square constant, so bring it out. And this is expectation and expectation of also cosine. We know that this one, expectation of cosine square, eventually it's going to be 1 over 2. We know that, right? So this is again constant, bring it out. Then we're going to get this one, AC divided by 2. So this is gone now. Now what is left over is this one. The expectation of this one, that's this part right here. So to do the calculation, we have a square here, right? Something square, a plus b square. So we can expand that, then a square plus 2 times ab plus b square, something like that, right? And then again, we calculate like that. Then eventually, we know that the output, this part, is going to be same as 1 plus ka square, the expectation of m squared t. Eventually, that's going to be the output. That's this one. And as we did before, this one is the power or energy of your own message. Your original message has its own average power. So this is the average power of your own message. We can simply put it as a P. So eventually put this one together. Now we know that AC squared divided by 2, 1 plus Ka squared P. So that is our signal power. This is how to calculate. Okay? That's our signal power. Yeah, this one. So this is our signal power. And we also need to know noise power, right? Then what was the noise power? Noise power, noise here, okay? We are talking about pre-detection, right? So pre-detection is happening right here, right? So it doesn't matter what demodulation you use, because demodulation comes later. So here, this is a passband. So when you look at the passband noise and take an expectation, this one is always not and not BT. This one is always and not BT. It doesn't matter what demodulation you use. This is the case we use a DSP. Right now we are talking about DC added amplitude modulation, right? But it doesn't matter. From this noise point of view, it doesn't matter because DSP or DC added modulation or single sideband modulation or FM modulation, all of those are different here at the receiver, right? Receiver is different. But this noise is measured at the passband, so it doesn't matter. Okay? Doesn't matter. So this is a noise power. In pre-detection noise power, it's always going to be this in pre-detection, because that's before the system, before the demodulation, right? So that's the noise power. This is a signal power. So simply we put this one divided by this. This one goes down to denominator. This one goes to here as a numerator. Then we can make a fraction like this, right? Then we get the pre-detection SNR like that. Okay, that's how to calculate the pre-detection SNR for this DC added amplitude modulation. So this is actually pretty simple, same as DSP almost. Okay. Now we also need to calculate the post-detection SNR for DC added modulation. This post-detection SNR, how to calculate is, again, we start from signal plus noise. And our signal ST is a DC added modulated signal, which means this one. So we have two terms, right? AC cosine plus AC Ka MT cosine. We have two terms in ST, right? So this one, we have two terms, AC cosine plus AC Ka MT cosine. So we have two terms in ST. For NT, again, we use the same technique and change this passband noise into baseband representation. Same way. We did that before, right? Same way. So we need to change this one into baseband representation. NIT cosine minus NQT sine. That's the baseband representation of your passband noise. Doing the same way, okay, and this XT, this whole XT now goes into our demodulator. Okay, and what is our demodulator in this case? Envelope detector is our demodulator. So put this signal, now put it into the demodulator, the envelope detector. So once you put this one into the envelope detector, what does envelope detector do? envelope detector simply detects the envelope. So in this case, you can see this, right? The whole thing, this one is kind of amplitude of cosine, right? You have cosine, and this whole thing is the amplitude of cosine. And this one is simply amplitude of sine. So when you have A cosine minus B sine, how do you calculate the amplitude or envelope? Simply, it's going to be A squared plus B squared. That's our envelope, right? So what this envelope detector do is this calculation. That's what happened inside the envelope detector. So same way, let's do that. This is A, kind of A, and that is B. So inside the envelope detector, this one square, right here, the whole square, plus this square. And put the root square of the whole thing, that's 1 over 2. Okay, that's what's happening inside the envelope detector. So this is what's happening inside the envelope detector. Now, but here, when you look at this, right? Okay, look at here. When you look at this, if the A is much higher, much larger than B, then as it says, it's almost same as A. So this is approximation. If the A is much bigger than B, then this whole thing is almost the same as A. So using this approximation, now we can change this into this. Okay, just A. Here's A, right? This A just pops out, and B just ignore that because of this approximation. Using this approximation, we just simply change this to this. Okay? So once you do that, what we now get is this is YT. What is YT? YT is here. We already passed the envelope detector, right? We already passed through the envelope detector, and the output of the envelope detector is Y. Okay? And what is the next step to do? In envelope detector, we detect the envelope. And what is the next thing to do? We remove the DC, right? In the earlier, we added the DC. So at the receiver, we eventually need to remove the DC, right? Remember that? So eventually, we are removing the DC. That's called the DC blocking capacitor, which means that we are removing the DC here. So we're going to do the same thing. So we get the YT as the output of the envelope detector, and we're going to remove the DC. So this is a YT, which is the envelope, which is the output of the envelope detector. Now we're going to remove the DC. What is the DC here? This is a DC, AC, right? This is a constant value. Constant means DC, right? So we're going to remove the DC. So what is after you remove the DC, now the output, eventually, output is going to be AC KA MT plus NIT. That's the output after you remove the DC. Right here, right here. Eventually go all the way through, and you get this signal right here at the output. Right here, right? Now it's time to measure the SNR, because we already passed the envelope detector and also DC blocking. So we've done all of this demodulation. So it's time to calculate the SNR. So this is the signal part, noise part. So we do the same way. What is the signal power, average power? So you do square of this, and then expectation, right? Expectation. But we know that this part is constant anyway, so bring it out, right? And expectation of m squared t, we know that it's always changed to p. So therefore, our signal power will be like this, right? This is our signal power from here. We know that, right? And noise power we did the same. Actually, we for noise power here in the post detection, this NIT, it's going to be 2 and not W. Why was that? This one actually we did it before, so let's go all the way. Actually, that's not in here. But the reason is, simply speaking, right? This W is the bandwidth of your filter. Because in the receiver, inside here, we have a filter, right? We have a filter, remember? And if you look at the coherent detector, you also has a filter. So receiver, inside the demodulator, you always has a filter. And each filter has a bandwidth, right? So this W is the bandwidth of the filter inside the coherent detector or inside the envelope detector. Okay, that's the filter. And typically, if you design a filter very well, this W is almost same as BT over 2. Okay, if you correctly design, this is going to be the bandwidth, typically. So given that W is BT divided by over 2, then you cancel 2, 2. Then it's almost same as N not BT, almost. So this is going to be the post-detection SNR. When you, not this one, actually, this one. This is going to be the post-detection SNR when you use envelope detector. Okay. So what this shows is the figure of merit. Figure of merit is the post-detection SNR divided by reference SNR, or in this case, pre-detection. So it's going to be K square P divided by 1 plus K square P, which means, let's compare this post-detection SNR with the pre-detection SNR. This is a post-detection SNR. And go back. This is our pre-detection SNR. In the pre-detection SNR, you have 1 plus K square P. This is a pre-detection. But in post-detection, you have this, right? So what does that mean? That means pre-detection SNR is large, right? Post-detection SNR is a little bit small, right? Is that correct? Actually, no. That depends on Ka, actually. Yeah, so let's see. Pre-detection SNR is K. Okay. This is a pre-detection SNR. And post-detection SNR was this one. Okay? So we have a pre-detection SNR of this much and post-detection SNR of this much. So if you compare these two, now let's assume that W is almost the same as BT over 2, because this W depends on the filter. Now, if you assume this, we can put this one in here, right? Then, if you do that, now it's going to be this, right? So we can compare this as a pre-detection SNR. This one is a post-detection SNR. So we can compare these two. Depending on the Ka value, if we use a Ka value like 100% modulation or less, right? Then we have a no distortion. But anyway, so these are the results. These are the results. It's hard to compare because we have 2 here, but there's no 2. But in this case, we have a 1 plus Ka square, but this one just Ka square. So it's not easy to compare, but that's the result. Pre-detection SNR, post-detection SNR. Okay. So that's how to calculate detection, pre-detection, post-detection SNRs. Okay, the next example is that we want to look at the single sideband. Okay, so we already looked at the double sideband and also this one, DC added amplitude modulation. Now we want to look at the single sideband. So this is a single sideband modulated signal. Okay, we learned the single sideband, right? We have an upper single sideband. We also have a lower single sideband. This is the case of lower single sideband, right? So when you do the lower sideband, lower single sideband modulation, this is the signal you transmit over the air. MT is our original message. M hat T is the Hilbert transform of your original message, right? And multiply the sine into the Hilbert output and multiply cosine into the original MT. So this is the signal you transmit over the air, right? Now we have this ST for single sideband. Again, in this case, we want to calculate the pre-detection SNR and post-detection SNR. Right? Simply, let's calculate the pre-detection. In pre-detection, this is a signal over there. So grab this signal and square, and then take an expectation. So let's do square over here. Okay? Because first thing to do is to calculate the signal power, average signal power. Right? So we need to so that is our lower single sideband modulated signal. In order to calculate the pre-detection SNR, the first thing to do is we need to take the signal power. That's the first thing to do. So let's calculate the signal power. We need to square of this and then take an expectation. Once you square of this, we know that it's going to be this square plus this square plus 2 times this and this, right? That's what you have when you do square of the whole thing. Now let's first look at the square of this. What do you get? You take an expectation, square and take an expectation. If you square this and take an expectation, what do you get? You're going to get AC square, because we are doing square of this whole thing, and 2 becomes 4. 2 becomes 4. And take an expectation of a square. It's going to be expectation m squared t. So we're going to call this one as a p, right? Same way. Now the cosine square and then take expectation. So we're going to get 1 over 2. So that's the square of this and expectation, right? Same way, we're going to take a square of this and take an expectation. Same way. Then what do you get? Again, same way, AC square divided by 4 and expectation of m hat squared t. And then sine square. What is the expectation of sine square? Expectation of sine square. Expectation of cosine square, it's going to be 1 over 2. Then expectation of sine square, same, right? It doesn't matter. Cosine, sine doesn't matter. When you square, average is same, right? Right? Yeah, cosine just go this way, sine goes this way, but when you square it, doesn't matter. It's the same 1 over 2. So it's going to be 1 over 2 here. Now plus 2 times this and this, right? 2 times this and this. Okay, let's multiply this and this, and then mt expectation mt m hat t, and also expectation of cosine, sine. You're going to have this term. As you can see here, here's some assumption we have. The two components mt and m hat t are uncorrelated with each other. This is one assumption you have. Okay, mt and m hat t are uncorrelated with each other. What does that mean? mt and m hat t are not correlated. So this is going to be 0. This one, expectation of mt, m hat t, this is the calculating. This calculates the correlation between these two, right? This is the original definition, how to calculate the correlation between these two. But it says these two are uncorrelated, which means this one becomes 0. That's what this means. Right? That's what this means. So based on this, now we know that this becomes 0. So we're going to ignore this whole thing. So we have these two. And another thing, the second term here, the Hilbert transform m hat t is something, but the squared magnitude of this transfer function is equal to 1 for something. So accordingly, mt and m hat t have the same average power p. That's another assumption, which means that this m squared mt and m hat t has the same original power. That's that assumption. Okay, so we have expectation, the time average, expectation of m squared t. We assume it as a p. So what is a p? P is the original power, average power of your message. Your message always go up and down. So there is an average power. That's p. When you take a Hilbert transform, we are getting m hat t. M hat t also like some other signal, right? That has expectation of m. That has some power, average power, right? That is also p. That's this assumption. mt, m hat t have the same average power p. Okay, this one is also p. That actually makes sense, right? Why? Because think about the Hilbert transform. What's the difference between mt and m hat t? Amplitude is same. Remember that? Only phase is rotated, right? Amplitude is same. Magnitude is same. So therefore, your power is going to be definitely same, right? Your signal has exactly same the amplitude. Only the phase changes. So the power, the original power of mt should be, of course, the same as original power of m hat t. Because the amplitude and magnitude is not changed, you should have the same power. Okay? So once you calculate these things, the third term now is gone. And the first term is ac squared divided by 4 p 1 over 2. Same thing here. ac squared 4 p 1 over 2. So therefore, ac squared p divided by 4. This is your signal power for single sideband. Okay, that's your signal power. Now, what was the noise power? Noise power is always this one. When you calculate the pre-detection SNR, right? For the pre-detection SNR, noise power is always this one. It doesn't matter single sideband, double sideband, whatever modulation you do, noise power is always this one for pre-detection. Post-detection, that's different, right? because your signal and your noise go through the demodulator. So now something is different. But pre-detection is before the demodulator. So this is a noise power, and we already get the signal power here. So this one divided by noise power, that's going to be our pre-detection SNR. That's our pre-detection SNR. Okay. Now, again, we need to calculate also the post-detection. Okay. And how do you get the post-detection SNR? Same way as before. The one technique we did was we're going to change the NT, the passband noise, into baseband representation, right? That's what we always did before, because in post-detection we need to look at the baseband signal. So NT is now changed to NIT cosine NQT sine. Okay, we need to change that. Okay, let me do that here. Okay. So we are talking about a single sideband right now, and let's calculate the post-detection SNR. Pre-detection SNR is pretty easy to calculate. Okay, pre-detection is pretty easy. Post-detection is a little bit complex. So let's look at post-detection. In post-detection, first thing is we are going to get the xt equals to this one. What is xt? Xt is a signal before the demodulator. So this is the signal, this is the input signal to the demodulator. Okay, so that is the input. Our input is xt, st plus nt. Nt is our passband noise. Now our st is this one because we use a single sideband, and noise is nt, but we want to change this passband noise into baseband representation, right? So therefore, let me change this. So our xt equals to this st plus our noise in baseband representation. That's going to be this. So this is our xt. So we have 4 different terms. 2 terms for st, another 2 terms for nt, right? Basically, we are doing the same thing again and again, right? Same thing again and again. For post-detection, the first thing to do is change the nt into baseband representation. That's we always doing, right? For post-detection. And st in our case is a single sideband, so we know that it's like this. This is for lower single sideband. So once you do that, now we know that this term and this term has a cosine, and this term, this one has a sine. Okay, and we know that this is xt. So what is the next thing to do about this xt? This xt now goes into our demodulator. So what is the first thing to do in the demodulator? Multiplying cosine. That's what you need to do, right? What is a single sideband receiver? What is the demodulator you use for single sideband? You're going to use the same receiver for the double sideband. Remember that? Single sideband is not special. You use the same receiver for the double sideband. That's going to be the receiver. And we use a coherent detector or Costats receiver for double sideband. So you're going to use the same receiver. Okay. So let's use a coherent detector. Okay. let's assume the coherent detector. The first thing to do inside the coherent detector is multiply the cosine. So we need to multiply the cosine here. That's the first thing to do, multiplying cosine. So let's do that. You are multiplying cosine, then it's going to be square. Again, square. Here, you multiply cosine. So you multiply cosine like this. Here also, you multiply cosine. Once you multiply cosine into xt, that is what's happening. Right? And what is the next thing to do? You're going to use identity. Because every time you see the square, cosine square, or cosine times sine, every time you see something like this, now you need to use identity and change this. So how do you change it? Cosine square, we always need to change into 1 over 2, 1 plus cosine 4 pi fct. We always have to change this. This one, sine times cosine, again, we always have to change it. This one, we always have to change it to 1 over 2 sine 4 pi fct. We always need to change that, right? So once you change the cosine square and the sine cosine into this one, now you're going to get this. This whole thing. Okay? You have a, once you do that, right? Let's look at here. When you change this cosine square into this, now we have this one as a DC term, 1 over 2 plus 1 over 2 cosine 4 pi fct, right? Right? So this one goes into here and also goes into here. Now we have that this term 1 over 2, this term 1 over 2. That's here. Right? Same way, you have this term times cosine 4 pi. This one times cosine 4 pi. That's right here. Okay? And also we have another term, sine 4 pi, and we have this one and this one. That's what's coming here. Okay? So we have these. Looks like a complex, but it's not really complex. It's like this. It's as simple as this. So that's what you see here. And now what is the next thing to do? Remember the coherent detector structure. You multiply cosine carrier, and next thing to do is low pass filter, right? So once you go through a low pass filter, what is happening is we know that cosine, this sine, all gone. Right? Or in other words, in here, this whole thing is completely gone. Now we only have this one. Right? We only have this one. That's the output right here. And that's the output of the coherent detector. Okay, we are doing the same thing again. So this is the output of the coherent detector. And when you look at the output of the coherent detector, we have two terms. The first term is a signal part. Second is a noise part. So since we have two terms, we can now calculate the SNR. So eventually output of the coherent detector is this one. That is the output of the coherent detector. Okay, that is the output. So we have a signal part. This is a noise part. Now, next thing to do is signal part square. Take expectation. That's a noise. That's a signal power. Expectation of this part. AC square. AC over 2 MT, the whole thing, square, divided by expectation of noise part, like that. That's our SNR, right? That's the output of our post-detection SNR. Okay? So once you do that, then you're going to get this output. not that difficult, right? It's not that much difficult. So always when you remember the post-detection SNR, okay, every time you look at the post-detection, first thing you remember, NT, the passband noise, you want to change into baseband representation. Baseband representation. Why? Because post-detection is always measured at the baseband, so you need to change it to baseband. Okay, so that's one thing to do. And all the other thing is pretty easy to do. Just use identity and then doing like this. Okay. Okay. I think we cannot finish this, but let's briefly discuss a little bit and continue next week. So we've done all the amplitude modulation. Okay, we looked at DSB and also amplitude added DC, the DC added amplitude modulation, also single sideband. Okay, we looked at 3 different modulation of amplitude modulation, and we calculated pre-detection SNR and post-detection SNR for all of this. Now it's time to look at the frequency modulation. Okay, FM. Okay, let's calculate the pre-detection and the post-detection SNR for FM. Okay, this one maybe in the post-detection SNR a little bit complex, but I'll tell you the main thing. Okay, the most important thing is you need to compare the frequency modulation case with the amplitude modulation. So let's start with the pre-detection, because always a pre-detection is easy. This is our FM signal. Remember that our FM signal looks like this. The amplitude is always constant. Our message goes into part of the phase, right? This is a phase component, and this is FM, so therefore you have an integration of your message. So this is our FM signal. That is a signal you transmit over the air. Now the pre-detection is that you just grab the signal over the air and then square, and expectation, right? That's what you need to do. So what is the signal? What is the average power of this? This is a signal over there. So grab this and look at the average power. So what is the average power of this? Okay, I think you're thinking, which means maybe you are thinking very complex one. But let's see. This is ST, our FM, and AC cosine looks like a complex, but this is a signal over the air. Just grab this signal and calculate the signal power. This is what you want to calculate, right? Signal power, average signal power. So what is this one? Just this. Why? Because this one is anyway just AC cosine. It doesn't matter whatever you have. Maybe you have something, but it doesn't matter. Okay, just square. Then you get the AC square and cosine square. What is the expectation of cosine square? 1/2. So it's like this, very simple. Because this FM modulation, amplitude is constant. Think about it, amplitude is constant. What is the average? Something in the middle, that's average, of course, right? The frequency, your frequency changes, but frequency change doesn't matter in the average power, right? Think about high frequency, slow frequency. What's the power? Same, right? Power is same, right? Frequency may be different, but power is always same. So when you look at the power, it always a function of amplitude. Frequency change doesn't affect your power. You see what I'm saying? Right? Simple way. I mean, look at the high frequency signal. Look at the low frequency signal. What is the average power of these two? This one, this one. This one, average power is this. Same. Okay? Frequency doesn't matter. So the average power of this is like a square, AC square, and cosine square, which is 1 over 2. So simply AC divided by 2. And what was the noise power in pre-detection? It's always this one, right? And not BT. Remember that? That is always the noise power in pre-detection. So the SNR in pre-detection in FM, it's very simple like this, right? It's very simple. AC divided by 2, that's your signal power, and not BT, so your noise power. So therefore, this is the SNR for pre-detection in FM. Okay, very simple. So it's very simple. Now it's time to look at the post-detection. Now it's a little bit complex because this is our FM receiver. So now let's look at FM receiver. This is where you add the noise, okay? And then here is you have antenna, something like antenna. You receive signal, and first thing to do is a bandpass filter, right? As always. You get a XT. This XT is the same as ST plus NT, right? ST plus NT. Now this ST plus NT goes into a limiter. What is a limiter? Limiter is something like you are clipping the amplitude. Okay, that's the limiter. So let me tell you what that means. We have a signal, right? What does the FM signal looks like? FM signal always has a same amplitude, but sometimes frequency changes like this, but the amplitude is always same. That's our amplitude, that's our FM signal, right? So amplitude is always constant, our FM signal. However, this ST is what we transmitted over the air. So FM signal always has a constant amplitude. Now we have a noise added. And our noise is added here. And our noise is like this. This is our noise. Once you add the noise into our ST, what is going to be the output? Your output probably has something like this, right? It's not flat anymore. It's not constant anymore because we have a noise. Noise is being added. So your amplitude is not constant anymore. Your amplitude maybe is going up and down a little bit, right? Because of the noise, right? Because you add the noise here. So your amplitude is not constant anymore. That's what you have here, somewhere here, okay? Your amplitude is not constant. So therefore, at the receiver, the first thing to do is limiter. And what the limiter does is when you get this, you get something like this, then what the limiter does is just cut it like that. Cut it. That's limiter. Just cut. And then remove this and this. We can do that. Why? Because in FM, the amplitude doesn't matter. Okay? Our message is inside the frequency, right? So amplitude doesn't matter. So we just cut it. That's a limiter. Just limiting the amplitude. That's a limiter. And once you do that, now the output of the limited signal goes into the discriminator. What is the discriminator? This is a kind of discriminator. Okay? And what is the mathematical function of discriminator? That's a time derivative. Remember that how to get this message? This is ST, right? We learned the FM. And how do you get this FM? How do you demodulate the FM? Take a derivative with this, with respect to time. Once you do that, this message brings out, right? That's this one, time derivative. So you want to bring the message out. Okay. Once you do that, we go to the low pass filter. Now you're going to get the output. So in order to calculate the post-detection SNR, now we need to go all the way through here, and we need to look at what the signal is here, and then calculate the signal-to-noise ratio right there. So it's a little bit complex. Okay, but we can continue next time.